here's the basic idea. We discussed already how 2D limits and 3D limits are the same and not the same. But most of the time, what we're going to ask is, does a limit exist or not? If it doesn't exist, that's usually the easier problem to answer. So consider this problem for a minute. Suppose I gave you f of x equals x times y over x squared plus y squared. And I said, what about the limit as x comma y goes to the point 0, 0 of this function, f of x? Okay. So again, the major difference in the 3D world is that when you approach a point, x, or in this case, we're approaching 0, 0, there are infinitely many paths you can approach 0, 0 through, right? Whereas back in the 2D world, we would approach a single number. Say, what's the limit as x goes to 5? We can only approach from the left or from the right of 5, and that was it. There were two limits to check. And now you have infinitely many, so it's going to be more difficult. All right. So what you got to start doing is thinking about paths that go through 0, 0. Well, the x-axis goes through 0, 0. That has an equation y equals 0. So we can ask ourselves, what's the limit as we approach 0, 0 moving along the x-axis? So it's the first limit we're going to do and see what happens. Okay? So we're moving along the x-axis. That really means y is 0. Our equation becomes x times 0 over x squared plus 0 squared, or 0 over x squared. Well, the limit as x comma y goes to 0, 0 of 0 over x squared is 0. And how do you know that? Well, as we pick any point really close to 0, 0, but not equal to 0, 0, the denominator is going to be some finite number, some decimal squared. It'll be something. And the numerator is going to be 0 stubbornly. It's going to be 0 divided by some decimal, which is going to give me 0. Okay? So what we know is if we approach the point 0, 0 along the x-axis, we're getting back z values of 0. And that's important to keep in mind. The answer to these limits are z values. Okay. So what's next? Let's try approaching along a different line. So what's another path that might go through 0, 0? Well, the y-axis does. And the y-axis has the equation x equals 0. So let's see what the function looks like. Now, it depends on how you write things. Sometimes you'll see textbooks write this. F of 0 comma y equals. So they're indicating that they're replacing x with 0 and they're leaving y alone. So it's 0 times y over 0 squared plus y squared, which is 0 over y squared, which is just going to be 0, no matter what y is, right? If y is some number that's close to 0 but not equal to it, it's going to be 0. Does that make sense? So far, you might say, hey, wait a minute. We approached along the x-axis, we got a limit of 0. We approached along the y-axis, we got a limit of 0. And you might start to say, hey, I think this limit might be 0. And this is where these problems get difficult, because you have to try all the possible paths. Now, we know we don't have time to do that. So I'm going to speed this up for you a little bit. I'm going to say, let's approach along y equals x for a moment. If we do that, then our function, which was the following, turns into, watch, it's going to be f of x comma x. Now, why is that? Well, we said y equals x. So I've replaced y with x here. The function then becomes x times x on top. And on bottom, you have x squared plus x squared. That actually simplifies. This becomes x squared on top over 2x squared on the bottom. And that's 1/2. Oh. Well. This is bad news and good news. Bad news because the limit doesn't exist. What we've just shown is that if we approach along the line y equals x, then the function gets really close to z equals 1/2. Okay? So that's, what does that mean? It means that it doesn't match up with the other two limits we found when we approach along the y-axis and x-axis, respectively. So since the limit from different directions isn't always the same thing, the total limit doesn't exist. So I say it's good news and bad news. Bad news because the limit doesn't exist. Maybe you wanted it to exist. But it's good news because now I don't have to go checking infinitely many paths to see if I always get 0 back for a z-value. Right. So here's a picture of this thing. Here's what happens when you graph it. What you can see is this like creased napkin part in the middle here. That's where the limit fails to exist. So what you can tell is that as I approach along this diagonal line, for example, if you follow the mouse, it's definitely from the left and from the right coming into the same z-value. It looks like they're approaching each other. And then maybe along this diagonal, they're doing the same thing, right? But then there are other places, well, just those two alone, for example. This z-value here that I'm pointing to, those two z-values are not the same as these two. So that alone is enough to say the limit doesn't exist. Okay? Back in the 2D world, you're used to limits not exist, meaning that from the left and from the right, you had a jump discontinuity or vertical asymptotes. You don't really get vertical asymptotes here. You get like vertical sheets, kind of. Like, you know, you get hyperboloids and things like that happen. Okay? So here's where things get interesting. What if a limit does exist? So let me show you a problem and then the following. So suppose I'm asking about this limit. Limit as x comma y goes to 0, 0 of 3x squared y over x squared plus y squared. And what I can tell you is that if you keep approaching along different paths, like approach along the x-axis, the y-axis, and so forth, that you're always going to get the same answer. And that answer you can find quickly. Suppose we approach along the x-axis. The x-axis means that y is 0. Well, if y is 0, the function becomes f of x comma 0, which equals 0 on top, because you have 3x times 0, over x squared plus 0 squared. So you get 0 over x squared, which is 0. So it turns out that this limit equals 0. Now, notice I am not showing that by checking the infinitely many paths I can dream up that go through that function. But I'm going to go through 0, 0 on the x and y axis and give you a z-value for that function. You can have fun with that. For example, you can start dreaming up functions that do things. Like, for example, try y equals x squared. Y equals x squared goes through 0, 0. My promise is if you make the substitution here and do the math and get the limit, you'll get 0. You could even use y equals sine x, because y equals sine x goes through 0, 0. Okay? And again, you'll get back 0, 0 as an answer. So I'm doing this just to give you a sense of, don't forget about y equals, well, we won't do that. Y equals the cube root of x. Sort of a fun one, that's right. I'm doing this just to make the point that there are really too many things for you to try and check. So what do you do in this situation? And that's what we're going to do next. We need a definition for limits in the 3D world, right? We know one from the 2D world. So back in 2D for a minute, right? We have the limit as x goes to a of f of x equals L. That limit exists if the following is true. If when x is within delta of a, then f of x is within epsilon of L for some delta and epsilon that are small and positive. Okay, and we have done plenty of proofs with that limit. We're going to change this into a definition of 3D. Here's what I want you to realize, that there's sort of another way to write absolute value of x minus a. You can write that as the square root of x minus a quantity squared, right? Because if you square something and take a square root, you remove its direction. If it's a negative number, it comes back positive, okay? So I'm saying this to you because then when I write the 3D definition, it might make a little bit more sense to you, okay? So let me show you. Ready? So here we go. So let's pretend we say that we have a limit x comma y approaching a point a comma b of a function f of x, y, and that equals some number L. Okay, so keep in mind, you're getting back one number, one z value, when you sub in these a and b values, or numbers close to a and b. All right, so that limit exists if we can do the following. If whenever the distance between my point x, y, and AB is small enough. So I'm going to write that this way. X minus A quantity squared plus y minus B quantity squared is less than delta. Then, see, and that's why in the previous example I went to the trouble of rewriting the absolute value this way, just so you can kind of see. It's analogous, right? When we go into the 3D world and we have two variables that we're plugging into our function, this is how we measure distance between them. We don't write it as absolute value. We write it that way using the distance formula. And we're saying whenever that distance is less than delta, then we can be promised that this would hold. F of x comma y minus L is less than some epsilon. So this is what changes a little bit. Okay. What I want to do is I want to take this definition and apply it to the limit that I told you was 0, and then proceed through the steps and prove the limit. That's going to be fun. Okay, so the limit that I claimed exists was this. The limit as x comma y goes to 0, 0 of the function 3x squared y over x squared plus y squared. And I'm saying that limit equals 0. That's what I'm claiming. So I am going to use that definition. All right, so if I want that definition, I'll just sub things in. For a minute here, I realize, hey, that's A, that's B, this is the function f of x, y, and this is L. So I've identified all those things, and now I'm ready. Okay, so what I'm saying is 0 is less than the square root. And this is kind of easy, because I plug in 0, x minus 0 is just x, so I get x squared, plus y minus 0 is y squared, is less than delta. Then that should imply that the following is true. The absolute value of 3x squared minus y over x squared plus y squared minus 0 is less than epsilon. So, here we go. This I can rewrite. It's less than epsilon. Okay, so now this is where algebra gets a little bit creative. If you think about taking the absolute value of this expression here, right? 3's absolute value is just 3, so that doesn't need to be inside the absolute value anymore. And neither does x squared, because whatever x is, x squared is going to be positive. So I can take that out too. This is sort of like the algebra of absolute value. Anything that's positive can just come right out, and you don't have to worry about it. Y, however, may or may not be positive, so I have to leave that in the absolute value. And then x squared plus y squared is a completely positive quantity. So I can rewrite the expression like this. Okay. Now, here's what sort of the magic is. Again, we're trying to get some expression that has epsilon in it and also has this, the square root of x squared plus y squared, because I want that to be less than delta, and then I can make a substitution and be happy. So I need to have some realizations here. So let's take a look at just this part of the expression, just that. X squared over x squared plus y squared. What you should ask yourself is there anything I can say about that? Right? Well, if you think about it, this is a fraction, and it has to be less than or equal to 1. Right? Let's think about that. This positive number on the top, the same positive number on the bottom, plus something extra. The smallest y squared could ever be is 0, right? So the biggest, I shouldn't say that, the smallest this denominator could be is x squared, which would make it equal to 1. Otherwise, it's going to be something less than 1. And then that tells me something about this expression. Then. What do we know about that now? 3 times this thing. Well, that's less than or equal to 3. Okay. So since that's less than or equal to 3, I can make the following statement. I can say that 3 x squared absolute value y over x squared plus y squared would have to be less than or equal to 3 times the absolute value of y. Now let's think about that for a moment. Let's make sure we believe it. We know that this part of this coefficient here is less than or equal to 3. So if that's less than or equal to 3, then of course this whole fraction here is less than or equal to 3 times the absolute value of y. So that's where we'll leave off. Now, this I can rewrite the following way. I'm going to use this trick again. You might say, why bother? Well, now I can make another inequality. I know that the square root of y squared would have to be less than or equal to x squared plus y squared. Now, this is just an algebraic convenience. I'm choosing this on purpose because this is the expression I desire to have, right? Well, remember, this thing is, this whole thing, what can we say about it, right? That would imply that if I choose delta equal to epsilon over 3, then we would be okay, right? Because what would that imply? If delta was less than epsilon, if delta equal to epsilon over 3, then this thing here, 3x squared x squared y over x squared plus y squared, absolute value, is less than epsilon over 3, right? And then if we follow the train of algebra back through here, we'll see that that holds true, provided we pick that. We'll end up with the following. We'll end up with this thing here being less than epsilon over 3, which means it's less than delta. That's basically what that's going to tell me. Then this is going to be less than or equal to epsilon over 3, which implies that this thing by itself is less than epsilon over 3. Oops, let's make my epsilon over 3 fine, which means that this thing was less than delta. So what did we say? We said that if you pick a particular epsilon, I can tell you how to get delta so that the limit exists.